All right, this time we want to quickly run through just a few of the more unusual data types, and then next time around we'll get into pointers, which will of course be one of the biggies. So what I want to look at here are hashes, unions, and sets. So the idea is, for hashes, this is the sort of associative array idea. We've seen this in Lisp. You've probably run across this in a couple of other languages if you've played around with them a bit. The idea is you've got a bunch of key value pairs to store. So I want to have a list of values where maybe I'll have a list of colors and associated red, green, blue values. So I decide, okay, I want to store red has value whatever. And then later on I decide, okay, I want to add green has value this, and blue has value that, and yellow has value this. And so as time goes on, you build up this list of keys, the red, green, blue, or whatever, that are unique, and then a value associated with each of them. So lots of languages will actually provide these as a data structure supported by a library or module, but some languages do have them as a built-in data type. Some of the things to consider: if you've got a typed language, of course there might be restrictions on the actual data type. You might have to go through and specify, okay, this key is going to have an integer type associated with it, or it might simply be that you can only store string types as as values, for instance, or maybe you can only store integers as keys. So you do need to be aware of the data type restrictions imposed by the language. The typical operations are obviously going to be updating a key associated with something, so adding a new key value pair, modifying the value associated with a key, possibly removing a key value pair. It could be the case that you want to be able to add new fields as you go along. That's pretty likely. We might want to be able to get a list of the keys or a list of the current values, or to be able to iterate through those, right? Those are pretty typical. So that's going to be kind of highly language dependent, just what specific kinds of things you can do, how much power and flexibility you've got. Behind the scenes, these are going to get implemented most of the time in some sort of searchable data type, right? You need some way to quickly go through, and if you've got this huge associative array or this huge hash table, you need some way to effectively go through and quickly find the value associated with, field X, or key X rather. So it's typically going to be based on an efficient searchable data type, B trees, for instance, whatever you might choose to use. So for instance, you're probably going to have one indexed on the keys, and it's possible that you're also going to have one indexed, a sort of secondary one indexed on the values. That's entirely possible. So I don't want to spend too much time on them, but just to bring up the possibility that those might be built into the language. Another one that we want to take a look at just briefly is the idea of unions. So for a dynamically typed language where the data type is just associated with the current value of something, you don't need to worry about having variables that can have different types at different times of your run. If I have a strongly typed language, or even just a statically typed language like C, where I decide, it would be really handy if at some points in the program my date variable D could have a string in it, and at other times it could have 3 ints in it, and at other times it could have something else. So the idea was to see if there was some way to specify that we could have different data types stored in this one item at different times, and do that without actually having to go to the length of using a record, for instance, where it would actually have storage space for an int, and storage space for a string, and storage space for whatever. Right, since if we're only using them one at a time, we really only need the memory space for whichever one of those is biggest. And so what they'll often do is use syntax that's similar to structs, where we'll go through and list the different data types that we want to use. So for instance, a day of the week or a weekday or whatever we want to call our data type. Sometimes it might store a string, sometimes it might store an int, maybe sometimes it stores something else. And so we'll give a list of these types And for each of them, we'll give a unique name that says, okay, when I want to access it as a string, I'm going to use this name. When I want to access it as an int, I'll use this name. So we then go through and create our variable weekday that could be, could at different times have one of these things. And then we use a sort of struct-like syntax to get at it, where we say, okay, in variable d right now, I want to access day as an integer. And then I can assign the value or read from the value or do whatever, treating it as an integer value. So again, the storage has got to be big enough for the longest type. And there are definitely some type checking issues to worry about here. If I was to go through after this step, where I just stored 6 in there, so I'm treating it as a 6 right now, so that's what's in the memory location. And in the next spot, the next time I use this, I try and access d as a string, what happens? Because obviously I've stored a 6 in memory there. That's not a string. And that's going to represent, I guess if I looked at that and it was the first character of the string, I'd think that this was whatever control character has ASCII code 6 in it. And then whatever garbage was after that until it happened to hit a null terminator, for instance, if we're talking about C. So there are some type checking issues to consider. Your compiler might be careful enough or stringent enough to go through and say, well, I'm going to keep track of what data type it's currently stored as. So it might have a hidden field in here as well, where it had 1 byte, say, that told the compiler whether right now it was stored as a string, or right now it was stored as an int, or right now it was stored as a whatever. In the case of C, that's not done. It's just up to the programmer to make sure that they actually store it in the way they intended. So you do have to be aware of what's happening behind the scenes if you're using these. Again, they're nowhere near as widely used anymore, simply because memory is cheap, and more often than not, if you want to be able to access it in different ways, you might actually store it as a record instead, where you have the string version and the int version each stored separately, and you just use whichever one you want at a particular point in time. However, it is something to be aware of. I did want to take a quick look while we're on the topic. And same sort of ideas we've been doing before, where we'll just play a little bit in C or C++ to see what these things look like. So for this one, it's the union layout file I've got there. So if we have a quick look inside there, what we've got are just a couple of quick examples of unions. So this first one, we've got a char int that stores a character and then an integer. And this is partly to play with looking at how this thing is actually stored in memory. How much space does it use? Where does it put these fields? And then the same idea for a double short, where we'll have a double and a short stored as this union type. So we'll declare variable x as one of the char ints and variable y as one of the double shorts. And all we're going to do is print the size of the fields. Right? So we'll print how big a char is, how big an int is, and then how big the union is. And hopefully it should just tell us that it's the bigger of the two, the size of an integer. And then we'll go through and look at the addresses and just see, is it using the first byte of that space as the char and the whole content as the int, or what's it doing? And then we'll just do the same thing with the other data type, the, what did we call it, double short, where we'll go through, look at the size of a double, the size of a short, the size of the union, and then where these things wind up stored in memory. So nothing too terribly fancy, but it does give you an idea. Okay, so we're up to date. So we're just going to run that and see what we get. So for a char is 1 byte, an int is 4 bytes, our union char int is 4 bytes. So it is indeed just storing it as the larger of the two data types. And if we take a look at the memory addresses it's using, it's kind of as we conjectured, where we're saying, okay, well, if I'm going to access it as a char, I'm just going to look at the first byte. If I'm accessing it as an int, I'm going to use the whole thing, but starting at the first byte. And if you go through and take a look, same sort of idea for the doubles, right? Doubles are size 8, shorts are size 2, and it's using the larger of those two sizes as the size of our union. And again, it's using the same memory address for each. So it's saying, okay, whatever it is, it's stored at the beginning of that space. So for instance, if it's a short, then we're probably just going to use the first 2 bytes. If it's in a double, then we're going to use the whole 8 bytes. Just in terms of the type checking, I forgot to talk about that when we looked at this. The type checking we've got going on here was the example I talked about before, where we're going to go through and play with storing a value in there. So we're going to store a value as a char and then look at it as an int, or store it as a double and then look at it as a string. So that's what the second part of that output was. In here, we store 1 in X as a character, and then looked at as an int, and it's 1. Hey, doesn't work out too badly because it's basically storing the ASCII value 1 in that first byte. A little more interesting for the second one, we stored 5.6 in that memory space as a double, and then when we try and view it as a short integer, we get this. So whatever the bit pattern is for storing 5.6 as a double, right, having the exponent stored and having the precision stored and all the weird formatting that goes along with that, those first 2 bytes wind up with this pattern as an int. So it gives you an idea of some of the weird things that can happen with unions if you're storing something as one type and then accessing it as a different type. And that's pretty generally true when it comes to typecasting in C. So, something to keep in the back of your mind as you're playing with stuff, but do feel free to experiment with some of this stuff and just see how it all works. All right, last of the data types I wanted to talk about in this little blurb is the idea of sets. Again, this is often provided in languages as a data type through another library or module, but a few languages will provide them as a built-in data type. Biggest idea here is it's the usual notion of sets, where you can take the unions of sets and the intersections and the complements of them, see if something is in the set or if something is not in the set, take the difference of sets. All the typical operations may be supported. It's a question of what operators you use for that. And the big question with sets is, how do you actually implement them? Right? If you have the idea of a set can be a set of anything, a set of integers or a set of real numbers or a set of chars or a set of whatevers, then there's no way for us, there's no way for us to know how big the set might possibly be, how many values might wind up in that right now. And some of the operations are going to get pretty expensive. But you could go through and take a sort of linked list style of representation for your set, where you say, okay, well, I'm just going to throw everything in there as a giant linked list, and when I want to perform an operation, I'll have to go through and see if, if I want to see if these 2 sets are the same, then I've got to go through for each element of the first set and see if it's somewhere in the second set. I can't really take a complement operation like that for a set, where I can't say, well, let's take everything that's not in this set of integers, for instance, because that would be essentially an infinite set. And of course, we have no way to store that. So there are some issues that come along with the representation that we pick. The other possibility is to go through and store it as a bit vector, where we say, okay, I'm going to have some fixed set of things that could be in this set. And for each of them, I'll have 1 bit that says, yes, it's in the set right now, or no, it's not. So that allows me to pretty quickly do operations on my set, where I can do unions and intersections and complements and things just by doing bit operations on these bit vectors, which can be done very efficiently. But that means that somewhere up front, I have to define, here's the universe of things that may or may not be in the set. And here's the bit vector and the ordering that corresponds to those. So here's the 60,000 integers that I'm interested in. Here's the bit vector of 60,000 bits, and you go from there, and just say, okay, for each bit corresponds to one of those integers. So not too widely supported, but you will run across it some. And of course, if you ever wind up implementing sets just as a data type, these are things you're going to have to address as well. All right, well, next time around we'll get into pointers, which should be the last of our major data types to consider. And then we will wrap up and move on to more possibly interesting issues in terms of control structures and whatnot.